Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Dinakar Jajati. Dinakar is getting his PhD at the University of Illinois in Urbana-Champaign. He's a student of Vikram Advi's. Dinakar is doing very interesting work on looking at traditionally unsafe languages like C and C++ and discovering interesting properties that you can verify. So I'm going to let him talk about SAFECode today, and please welcome Dinakar.
Hi everyone. I'm going to talk about the research I've been doing at University of Illinois for the past 3 or 4 years. We have built a system called SAFECode, which stands for Static Analysis for Safe Execution of Code. And the title of my talk is SAFECode, a platform for building reliable software in unsafe languages. Well, we all know that software has become pervasive. We are using it for everyday applications, mission-critical applications, and commercial applications, and so on. And no matter what the domain of software usage is, unreliable software can cause a lot of damage. For example, the code red worm has reported to have caused up to more than $2 billion loss. Okay? So regardless of the domain, there is an increasing need for building reliable software. But in practice, a majority of today's applications are written in what are known as unsafe languages like C and C++. Okay? These languages have weak semantics, and which in turn results in a lot of undetected memory errors, such as array bounds errors, dangling pointer errors, typecast errors, and so on. Okay. This failing of undetected memory errors has 2 major implications. The first one is that attackers and hackers can take advantage of these undetected memory errors and gain unauthorized control of systems. Okay. Yes? Yeah, pointers to free memory. And the second thing is that any sort of analysis that you want to do on programs written in C and C++ is suspect, because most verification tools assume absence of memory errors. Okay. But there is an alternative to C and C++, which is the use of safe languages. And safe languages have sound semantics as opposed to C and C++. Now, once you have sound semantics, you can use any program, you can use all these verification tools to do a sound analysis. Okay. And safe languages detect memory errors. In particular, they detect bounds errors. And they have no dangling pointer errors, no pointers to freed memory, because they make use of garbage collection to recycle memory. And because they have no undetected memory errors, security violations due to memory errors doesn't exist in case of these safe languages. Okay? But there is a flip side to using C versus Java, or these safe languages like Java, C#, and other safe dialects of C, including CQt and Cyclone. That is, there are no hidden performance issues when you use a C program. So some programmers like that. In case of the languages like Java, C#, there are some hidden performance issues, particularly dealing with garbage collection, which could lead to increase in memory consumption or response times or performance. So some people generally don't prefer to use this. But in either case, why can't we port existing applications which are written in C and C++ to these strongly typed safe languages? Well, the answer is porting is not easy. Right? So the main reason, one of the main reasons supporting is not is that of automatic memory management or garbage collection. Now, these C programs are written years ago. They're never written with garbage collection in mind. So if you want to throw in a garbage collector, or add in a garbage collector to a C program, you have to tune it. You have to tune it for memory consumption. And besides, precise garbage collection for C and C++ programs is tough, because of the type unsafe nature of these programs. The second reason is that some of these safe dialects, including CQt and Cyclone, require metadata and pointers to deal with the problem of pointer arithmetic. Right? This metadata complicates interfacing with existing libraries. So what you have to do is to use wrappers in order to use these systems in the presence of existing libraries. So the bottom line is that porting your applications to safe languages is not an easy task. Now, our solution is essentially a SAFECode platform. SAFECode is a compiler and a runtime system, and it works in two different modes. In the first mode, SAFECode defines sound semantics for C based on some criteria which I'm going to describe later on, but it doesn't detect few memory errors. In this mode, SAFECode is completely automatic. It doesn't require any wrappers. It doesn't use garbage collection, and works for nearly all C programs. And it has a low overhead. We found less than 30% in our experiments. And since we're able to define sound operational semantics for C based on some criteria, we are able to provide a sound analysis platform for C programs now. Okay. But in this mode, SAFECode doesn't detect two errors. Especially, it doesn't detect dangling pointer errors. It doesn't detect array bounds errors. But it is able to mask them in such a way that it is still able to provide some useful guarantees. Okay. There is another mode to SAFECode in which, again, you have sound semantics, and it's able to detect all memory errors for C, but it works only for some applications. For others, the overhead is just too high. Okay. In this mode, SAFECode is again completely automatic. It doesn't require you to write any wrappers. It doesn't use garbage collection, but it detects dangling pointers online for some applications. Okay. And it is able to detect bounds errors with no pointer metadata for all applications. So the way we envisage you to use this is use this mode to do your development, debugging, and testing. And if you're okay with the overheads, you can even use it for production code. Okay? But if the overhead is high, you can always fall back in this mode where you get some guarantees. Yeah. Sound for nearly all C programs. There are some programs for which it doesn't work. So C has weak semantics in the sense that in the type system of C, you cannot prove that it cannot detect arbitrary memory references. So in our case, you mean type C? Yeah, in our case, we are able to prove that despite the presence of memory errors, it doesn't dereference arbitrary memory locations. So you could have a memory error like a dangling pointer error or a bounds error, but it's not going to dereference arbitrary memory locations. It's going to dereference only few memory locations which are defined by our semantics. Okay. So the three main research contributions that came out of this work, one is this sound analysis framework for C, which works without detecting all memory errors, and the two others are what I've just talked about. One is bounds checking for C programs with no metadata. And the final thing is efficient dangling pointer detection for some programs. Okay? And this is the outline of my talk. I've tried to motivate the problem and gave an overview of SAFECode. Now I'm going to discuss the first part of my talk, which is the sound analysis platform for C without detecting all errors. Then I'm going to focus on these two bug detection approaches, then talk about some other work I have done, and finally conclude. Okay. So if you look at how software analysis tools work today, they take a C program, use a normal compiler, extract out information like alias analysis, call graph, and type information, and then you can feed to this tool your original C program, alias analysis, and the property that you want to verify. And the tool comes out with an answer, yes or no. Let's say the tool comes out and says yes. Does it mean that the program satisfies this property in all execution environments? Well, it depends. It depends on whether the alias analysis is invalidated at runtime or not. Right? In particular, as I'm going to show later on, if you have errors in your program, if you have bounds errors or dangling pointer errors, they may invalidate alias analysis and call graph. Okay, and here is our solution works. Well, basically, we're going to use the normal compiler to extract out the same alias analysis, call graph, and type information. And the SAFECode platform takes in your original C program and this alias analysis, and out comes a new C program with some sort of checks. And these checks make sure that the program never deviates from the alias analysis. Okay? Now you can feed in this new program with these checks into your favorite software verification tool, and you can get an answer yes. And if you get an answer yes, it really means that the program satisfies that property in all executions. Okay? In particular, what SAFECode does is take this alias analysis and call graph and enforces it on the program. Okay? And I'm going to give a one slide background on what alias analysis is. Alias analysis is just a static summary of memory objects and their connectivity. And I'm going to describe this with the help of an example. Let's say you have a function, make list function, which creates a linked list of 20 objects. One way to statically summarize the memory objects that are present in this program is to use a graph like this. You have a head pointer pointing to this node in the graph, which has this type struct list. And the next field points to itself, basically summarizing all the 20 memory objects that are part of this linked list. So if you had even million elements here, you would have summarized it in the same way. Okay? So for those of you who are familiar, the alias analysis that we use here is a flow insensitive, unification based, and field sensitive alias analysis, which could be context sensitive or insensitive. Okay. Another example is here. You have an allocation here of an array, which is once used as an array, and then you type it to some other, to typecast it to some other type, and then try to use it as that type. In this case, alias analysis will not be able to figure out what the type of the objects that are involved there. So it's going to mark it as a TU, which stands for type unknown. So alias analysis in some sense partitions all the memory objects of the program into these TK nodes for which it is able to infer the type, and these TU nodes for which it is unable to infer the type. Okay?
So is it true that the common alias analysis folks use like class or slang, they make use of the type structure?
They may not make use of the type structure, but they will definitely use the connectivity. So the fact that next points to itself is something we might use, or the fact that the next might not point to itself, might point to something else, and they might use that connectivity information.
But for example, there are some physical tasks,
Okay.
and the same piece of memory is sometimes referred to as left, sometimes referred to as G.
Okay.
Then what sensible alias analysis make of that?
So yeah, alias analysis has to be conservative. So it basically says that I don't know what the type the programmer intended, and so it's going to mark it as type unknown. I'm not exactly sure what the verification tools do in such a case.
But for example, Mallory's alias analysis does mark that type unknown. Are you talking about one particular alias analysis?
So some alias analysis do not figure out the type information, but they can be easily extended to do so. I am not particularly aware if Manavir's alias analysis figures out the type information or not, but you can easily extend a alias analysis which has these properties to also infer the type information. Okay. Let's assume that after this class you use it as the field 8 of this structure queue, in which case you have an array of only 2 elements and you're trying to access the 8th field here. So this could in fact be a memory error. Right? In particular, this could override the next field of some element here, and the next field might point to somewhere else in the memory. Right? So this means that alias analysis is sort of assuming that there are no memory errors and try to get some conservative representation of the memory objects in the program. But in fact, if there are errors in your program, your alias analysis is incorrect. Okay? Now let's go back to our, yes? Sure. So yeah, it doesn't. Here you are updating field 8 here. So it assumes that the allocation can hold up to 8 elements. If you can do that, then the only conservative alias analysis you can get by taking into account all the memory errors is something which says that everything points to everything, which is not really useful. So let's go back to this problem of enforcing alias analysis. We have, let's say, this temp pointer pointing to this node here, and this node could actually correspond to million objects at runtime, and we want to make sure that temp points to one of those million objects at runtime. Okay, and if you use a naive normal memory allocator, all these memory objects are going to be scattered around in the heap, and if you want to do a runtime check that temp actually points to one of these million objects, it's going to be extremely expensive, right? And the way we are going to approach this problem is basically by making use of a previously developed compiler transformation called automatic pool allocation. Okay? And here is a one slide background on automatic pool allocation. This is developed earlier in our group by Chris Latner and Vikram Adve, and it appeared in PLA 05. And essentially what it does is partitions the heap of the program into pools based on alias analysis. Okay? Each node in the alias analysis graph is going to use a separate pool of memory. And once a pool becomes inaccessible, you can completely destroy the pool. So let's go back to one of the examples. Let's say you have two nodes in your alias analysis graph, one pointed to by head, another pointed to by x and y. If you use a normal memory allocator, they're going to be interleaved in this manner. They could be interleaved in this manner, right? But if you use pool allocation, what you could do is take all the memory corresponding to this node, put it in one pool, and take all the memory corresponding to this node and put it in a different pool. Now, your heap will look something like this. So all the memory corresponding to pool 1 is going to one part of the heap. All the memory corresponding to pool 2 is going to go to another part of the heap. Okay? So we have segregated the heap into pools. And now all the memory corresponding to one alias analysis node is in one part of the heap. Now we can do our checks relatively easily. Okay? So the check is simple. So if you have a pool is organized as a list of pages, each of size 2 per k. Right? And pool maintains a hash table of the start address of the pages. Now when you want to do a runtime check that p points to this pool pp, what you need to do is just mask the lower k bits of p and see if it's in the hash table. And you have to do other alignment checks. Okay? So a pool check is efficient now, but still it involves a hash lookup. Yes. So your program could have TK nodes or TU nodes, right? The TK nodes, for the case of TK nodes, all the objects in the pool are type homogeneous, right? In case of TU pools or TU nodes, we don't know the type of the object. So there could be different types interleaved with each other. So it depends. So if you have a TK pool, pools are type homogeneous. And you can do alignment checks easily. Okay. Now, we want to reduce the number of checks. Right? If we want to do this pool check on every pointer access or pointer initialization, it's still going to be expensive. So we want to reduce the number of checks that we want to do. And one way is basically we eliminate most checks for pointers that you read from type known pools. And the way we do it is by taking care of all errors for TK pools. Okay? We ensure that each memory error, in case of a TK pool, does not invalidate alias analysis. Okay? And I'm going to go into one such error, which is dangling pointers to freed memory. I think this is interesting because it's a very hard problem. And here is an example. We have two pointers P and Q. which become aliased at this point. So your memory could look something like this. So P and Q point to the same memory location, right? And you have freed P, so Q becomes dangling, and there is a dangling pointer usage here. The reason why dangling pointer usage is a problem is because if you have an allocation before the dangling pointer, let's say allocation R, and the system decides to allocate R on top of the previously freed memory. Now by trying to use this dangling pointer, what you're essentially doing is taking this arbitrary value here, casting it to the type of QRNX, and trying to use that. So this is a type error in some sense. And this will invalidate alias analysis for the same reason as type errors. Okay. Now our solution is this. Basically, let's say instead of allocation R, we had an allocation S, okay, which has the same type as P and Q, and which has the same aliasing properties as P and Q. Okay. Let's say we decide to we allocate S right on top of the previously freed memory with the exact same alignment. Okay. Now Q and S have the same type. So Q arrow next and S arrow next are going to have the same type and the same aliasing properties. So even if you do a dangling pointer usage, you are not going to invalidate alias analysis. Is that clear?
As long as you say that you can be used to S,
Yeah.
you are being,
Yeah.
but why should that be the case? So
This,
the code on the left, right?
yeah.
By examining, from my very vague knowledge of data science, it won't say that you can be used.
Not in this example, but if you could figure out, if you had some allocation which was alias to P and Q, right? Then if you decide to reallocate that allocation on top of the freed memory, you are fine. This malloc is already present in the program. So P of P with S. I am assuming that P, Q, and S have the same aliases. So that's what the alias analysis has given me. Let's say we had some other instruction here or later on which says Q equals S. In this snippet of the code, it may not conclude, but it depends on what's there in the next. So my alias analysis is the flow insensitive alias analysis. So even if you do something else later on, it will conclude one alias graph for the program. So it's not, the alias analysis doesn't depend on the points in the program. So there is one alias analysis graph for the entire program. So even if you do something later on which makes Q and S alias, then we can't take this approach. I mean, we cannot reallocate on top of the previously freed memory. Okay. So, but the idea here is that in case of TK pools, they are already type homogeneous. They already have the same aliasing information, right? Then we can use this technique, right? We can allocate previously freed memory to new objects with the same alignment, and we're able to take care of any alias analysis problems. Okay. But we have to place a restriction that until the pool becomes inaccessible, we do not release memory from the pool. This may lead to increase in memory consumption in some cases, but we found in our experiments that for 17 embedded programs, only in one program there is an actual increase in memory consumption. Sure. Yeah. We do not release memory to the system. We just keep it with the pool and use it for other allocations that arise for the pool. Yeah, that's yeah, yes. It's not just by type, it's more fine-grained than type. We are going to base it on alias nodes itself, which have the same type. The program is wrong, but we want to make sure that the program never deviates from the alias analysis. Now, if you can detect dangling pointers, in some sense, no, when you do alias analysis, you kind of assume that there is no free in the program. You kind of assume that all allocations are and they're infinite heaps. There are no bounds errors. So what we are trying to make sure is that once we do that alias analysis, we're never going to deviate from the alias analysis. Right? Yeah, we don't know whether the program is giving the right answer or not, because there is no definition of right answer here, because the program already has a bug in it. It has a, yeah.
What you're saying is the problem. Earlier approaches to alias analysis were also because they were operating on a wrong program. Basically, they were making all kinds of assumptions on the program without actually thinking of the program. Now what you're doing is you're actually enforcing those assumptions by putting this research statement. So at the end of it, you get an alias analysis, you get a modified program, and then the two are consistent with each other.
Yeah, so the asset statements are put for only few of the errors. In case of dangling pointers, we just do it using a runtime technique. So essentially, there is no overhead involved. We make sure that even if you access dangling pointers, you're accessing something that has the same aliasing properties. Yes. Yes, I'm going to come to that in a little bit. Yeah, it's a static analysis. We are going to do escape analysis on the alias analysis graph and figure out when this certain portions of the graph become inaccessible from outside a function, and then we can bind the lifetime of the pool to that function. If it escapes a function, we try to bind it in the parent function. If it escapes that, we try to bind it in the parent function of that function. So in some cases, it's possible that it escapes all the way, and you have to put a pool in the global in the main function. Embedded program. Yeah. So you go to the topmost level and try to put a bound there. If you can't, then you can even make it a global pool. So in case of other memory errors like array access errors, like say A of I, we're going to check that A plus I belongs to the same pool as A. Now this is different from a bounds check, because that pool can have 2 or 3 different arrays. What we are checking is that after arithmetic, we are pointing into the same pool or not. We're not checking a pointer points to the same array or not. In case of typecast errors, these are essentially going to end up as TU pools, and we do a runtime check on all pointers that you read from TU pools. Or here TU means type unknown. So if you have a typecast error, it's going to end up as a type unknown node in the alias analysis graph. And it's going to have a type unknown pool after automatic pool allocation. And all pointers that you read from TU pool, you're going to check at runtime. In case of pointers, dangling pointers to stack location, these occurs when you have pointers pointing to a function activation record after the function written. What we do is try to conservatively prove that there are no such dangling pointers. If we can't, then we move the stack allocation to a heap allocation and do what we did for the heap. Yeah. Yeah. true, but I'm going to show later on why the whole thing is consistent with each other. Now you might think that this has a circular argument, right? But I'm going to prove that our approach has no holes, essentially right after this slide. So in case of uninitialized pointers, we use hardware checks, which is actually used in most debugging tools, or we have to do explicit null checks like in Java. Okay? Essentially, only array accesses, array checks in case of TK pools get runtime checks. And in case of TU pools, all pointers that you read from TU pools will have runtime checks. And by this, we have ensured that alias analysis is never invalidated. And like you mentioned, this may have some holes in it. We might not have taken care of all the checks, or we are based on a circularity argument. Right? Now, the way we solve that is basically formalize everything as a type system. Sure. To some address of base of resort addressing, yes. At least all the pointer fields. So another way to think about this SAFECode approach is that it's taking this C program, it's taking this alias analysis and call graph and type information and so on, and does this automatic pool allocation transformation. And what we are going to output is a program in a new language which has the same syntax, which has some same statements as C, but it has this new pool constructs. And it has alias information which is encoded as type attributes. Okay? Now, we're going to define static typing rules for this new language, which basically check that the alias analysis you have encoded using these type attributes makes sense. Okay? And we're going to define operational semantics for this new language, which are based on this aliasing information in pools. These operational semantics include all the runtime checks that you ever need to do when you're running the program in this new language. Okay? And then we are going to prove a soundness theorem, which states that the alias information encoded in this type system is always going to be valid, regardless of the fact that there are memory errors or array bounds errors or dangling pointer errors. Okay? So you do all this, get this new program, just type check it, then you're sure that the program never deviates from alias analysis. Okay? So essentially what we have defined is basically sound operational semantics for C based on this aliasing information and pools. Here is an example, and I'm going to show how this example looks in our new language. We have two pointers x and y, which become aliased at this point. So x and y point to this node in this graph, which is of type int. And we have z, which points to a different node, which again has type int. Let's call this node row, and let's call this node row prime. The way we encode this aliasing information into the program is basically by adding this node attribute to each of these pointers. So x and y now have the type int star row, and z has the type int star row prime. Now when you have y is equal to x, it will type check because x and y have the same type, because they point to the same node. Right? But if you had y equals z, it won't type check because y is equal to z have different types, even though both are same int star pointer. Okay? We are going to replace all mallocs with this pool alloc, which will essentially allocate out of this memory allocated out of the pool. We're going to replace free by a pool free. And we are going to bind the lifetime of these pools using this pool init statement. So essentially, at the end of this pool init statement, we can completely destroy the pool. Within this scope of this pool init statement, we can reuse as much memory as we want using this pool alloc and pool free. Okay. Essential idea in this encoding is that if two pointers have different types, then they are not alias. Okay. and the pool allocation transformation, which is going to give us this where to place this pool in. So union scores are going to end up as TU nodes or type unknown nodes. And they're going to have a pool which is going to be a type unknown pool. All pointers that you load from a union, you're going to check at run. What? No, we don't. Check that the pointer points to the appropriate pool. So in the case of TU pools, what we are doing is like a coarse memory safety check. We cannot do anything fine-grained than that because we don't know what the type the programmer intended. So if you have an error, which is in case of TU pool, we won't be able to detect it. But once you load a pointer out of TU pool, and say if it points to another TK pool, we're going to check it and make sure that from that point on, the program is correct. No. If you have a pointer arithmetic, it'll try to infer the type as the element type of the pointer. The alias analysis typically do that. It's not something I've come up with. Yeah. So we have 2 divisions instead of these 3. So we have this TK or type known for which we are able to infer type, and this TU for which we are not able to infer type. So the TU is analogous to wild pointers in C. So in this talk, I've only focused on the enforcing how we enforce alias analysis. But we can enforce call graph in a similar manner by checking all operations to all indirect function calls at runtime. So the way call graph is typically represented is by making sure by having targets for each function pointer. So the call graph analysis will say that this function pointer could have these 4 or 5 targets. The way to check it at runtime is make sure that that pointer actually points to one of those 4 or 5 targets. A naive way is to check everything at runtime, but you could have some static typing rules which will eliminate some of the checks. Yeah, in case of checks for pools, we don't need metadata because the pool itself is giving us some information, right? The pool itself tells us what the type of objects are there, the type of the objects that are present in the pool. Not for TU pool, right? Yeah, not for TU pool. Yeah. So if you load a pointer from a TU pool, we're going to check before you use that point. We need to statically know all the possible targets of that pointer. That's what the call graph analysis typically gives, right? The call graph tells you what are the possible targets of a function pointer. Now we just want to make sure at the runtime that it is indeed calling one of those targets. So even when you have TU polls, alias analysis typically is able to figure out all the possible function targets. It won't tell you exactly which one it is, or it won't tell you what the type is, but it'll tell you, what are the function targets, because there are only so many of them in a program. Right? Sure. So as long as it has the properties of flow insensitivity, unification based, and field sensitivity, we are able to guarantee that alias null. We don't care how you generate the alias null. It has to have those properties. And in fact, in most alias analysis that are used by verification tools have these properties. Right? They are flow insensitive. They are unification based.
I mean, the thing is that I think he's doing something very clever, something, making all kinds of assumptions about booleans and structs, so on and so forth, assuming that everything is somehow well timed or something like that. So I might not be doing something as coarse as you might imagine.
Yeah. So
It's still flowing sensitive, but I'm making all kinds of typing assumptions, and I'm hoping that somebody will use the appropriate typing. So I have a feeling that you are assuming that the alias now is doing something stupid enough for you to be able to make it sound.
it's not stupid. I wouldn't call it stupid. It is, but that is the alias analysis that most compilers use. So
Okay.
a flow insensitive unification based analysis is what scales for the program. Yeah. So, well, you could use a different alias analysis and make sure that at least you have some guarantees, and then try to use our semantics to reason about shape analysis. For example, here, so let me just go forward to one more slide. So here is an example where we have a malloc. Like we have q equals p in this part of the if branch, and in the else part of the branch, we have a free and another malloc. Okay. Our alias analysis, since it is flow insensitive, it's going to assume that q is equal to q and p are aliased on all paths. But in particular, in the else part of this branch, p and q are not aliased, right? So if you want to do a flow sensitive analysis using our semantics, you have to make changes to your analysis. You have to make changes to what you think about malloc. So you have to change the malloc semantics of the program. In particular, you have to assume here that p and q could be aliased because p and q are put in the same pool. So I believe this is a local change that you need to do when you reason about malloc in your analysis too. Yep. Well, so the reason why we wanted to make sure that you can only we were able to make sure you can only handle field insensitivity or flow unification based analysis, for example, is because we don't want to have metadata for pointers. If we can add metadata for pointers, then we can make sure even fine-grained analysis which is non-unification. Right? No, there is a tension here that you don't want to have programmers report their applications to your new system versus giving them some guarantees. Right? Now, if you're able to ask programmers to report their systems to new application, you might not want to even use our analysis. You might even ask them to report their applications to Java, and you're fine with it. So, well, the soundness theorem that we prove is that a well-typed program will always go from one well-typed state to another, or will fail on one inserted runtime checks. Essentially, the proof is by induction on the structure of the typing derivation. And this guarantees that the alias information that you have encoded in the type system is never invalidated because of any error that you have in your program. Okay? And I've already talked about this slide, so I'm going to skip it. So the conclusion here is that you can do sound analysis for C now. they could be either flow sensitive or flow insensitive. You just need to make changes to the malloc semantics in your software analysis code. Yeah, I'm gonna. Yes. So we evaluated our system on certain benchmarks like Olden, pointed disk, and few system software like daemons, and we found that we didn't have to make any source changes. It completely works out of the box. And the overheads are here. So this is a table with here we have listed some programs. I picked some from Olden. This is from pointed disk, and this is one of the daemon. This is our slowdown ratio. The maximum overhead that we found was for this program here, which had like 30% slowdown. In average case, it is much better. In fact, one thing I need to mention here is that pool allocation by itself is proposed as a optimization for memory hierarchy performance. So pool allocation actually improves the performance because we are able to collocate objects of the same alias at one particular place. So the overhead that we have, basically in some cases we do even see a speed up because of that reason. This one's it's the bounce checks. For arrays, we still do a check, right? And these checks involve hash lookup. Even though we do some caching and some performance improvements, but still we hit some. Yeah. Yeah. So in this case, we have the numbers in the paper. I don't remember offhand for this program. But in average, the overheads are not much greater than 30%, even if you take the pool allocated version. It depends on the program, and it depends on the strength of alias analysis too. So if the alias analysis is better able to segregate data structures, then you would get a lot of improvement. Well, and that paper in PLA 05 has the detailed performance result. But in most cases, they found that pool allocation actually improves the performance. It never degrades the performance. It improves. In few cases, it's able to improve like up to 50% because of this co-location of data structure. It depends on how the program is written. If you're using mostly type-safe features of C and don't do arbitrary casting or don't use unions, for instance, then you get everything as type known. It is also dependent on things. You're right. So if your alias analysis is good, then it probably is able to figure out most things as type known, and if it's not, then you'll have more to union. Yeah. So
they had to make changes and make it back to the
yeah.
So they observed that even in C people often programming is arbitrary in particular class before it started.
Yeah.
And so if you have to automate those types of things,
No. So the reason why in our approach that's not a problem is because of the strength of alias analysis. The alias analysis that we use, it doesn't infer aliasing information based on casts. It will infer information only based on the usage. So if you take some pointer, cast it to white star and cast it back, then it wouldn't create a TU pool, or it wouldn't mark it as a TU node. Unless you use it actually as two different types, it wouldn't mark things as TU. So there is some cost to doing this in this way. So secured is like what they call intra-procedural. So it does everything within a function. But the alias analysis that we are talking about is like inter-procedural. So you need to have the source of all the program to do this alias analysis. So we did compare with SAFECode on this olden set of benchmarks. We downloaded SAFECode and ran our test cases. And for the same programs, the overheads were like much worse in the same system. Okay. This is just to give an indication that our slowdowns are good even though we don't detect dangling pointers and array bounds errors, and SAFECode does. SAFECode is a much stronger system in that sense. But their overheads are a little bit worse here. Well, in order to run SAFECode on these daemons, you need to write wrappers. And we weren't willing to do, we didn't know, basically we didn't do that. It takes some time and effort to port your applications to this SAFECode. And in fact, in case of these programs, SAFECode had to do like 100 lines of changes where we didn't have to do any source change. Yes? So in conclusion, we provide sound operational semantics for C based on alias analysis. We can guarantee that alias analysis with low overhead. We can guarantee that a program never deviates from alias analysis with low overhead. And we also guarantee memory safety. By memory safety, what we mean here is that program is not accessing memory outside its data area, and program is never executing code outside its code area. So we are enforcing some stronger notion of alias analysis. So this automatically comes from that. The two errors that we don't detect are this array bounds overflow and dangling pointer dereferences. And in the next part of my talk, I'm just going to discuss briefly about these two techniques. So we all know what the problems with array bounds overflow is. This is one of the most common reasons for security attacks. Over 50% of the attacks that are reported by CERT, an organization that keeps track of all the security vulnerabilities, are because of buffer overflow. Right? And the first exploit based on array bounds was reported in 1988. And if you look up Bugtrap now in 2006, you continue to see exploits based on buffer overrun, which suggests that this is not like a solved problem. The problem is simple. When you have pointer arithmetic in C, you don't know the target array of a pointer. Right? So here is an example. We have a pointer q, which is coming in for the function here. And we're trying to index into this pointer q. Now q is already comes out of another pointer arithmetic in this invocation of foo. Essentially, q is pointing to an array at some middle of an array. And from this pointer, we cannot get the p value. But we don't know what p is in order to do a runtime check. Okay. And most of the previous solutions are based on the fact that you can maintain metadata with each pointer. So for each pointer q now becomes q and p. Right? Now once you have this start of the target array of each pointer, you can do a runtime check just like in Java or C#. Okay? By just taking the second part of this order pair. So the main what? Usually allocations store length before the array starts. So that's what Java does. But there is a problem of backwards compatibility. If you want to take this approach and use it with existing C programs in presence of libraries which don't expect metadata, then you have to write wrappers for each library call where you strip the program of the pointers of their metadata and pass in the original pointers. And when you get back pointers from the library call, you add in this metadata. Okay? So this sort of complicates interfacing with libraries, and most of the porting effect in SAFECode is because of this. Okay? There is one backwards compatible solutions to bounds checking, which is based on Jones Kelly's work, and I'm going to go a little bit more detail because our approach is based on this. The idea here is simple. Whenever you have an allocation, you're going to store it in a global table. Right? You're going to register all allocations in this global table. So if you have allocation for P, you're going to store the start of P and the size of the allocation. Right? And whenever you have a reference, like a pointer arithmetic here, and whenever you have a pointer arithmetic, you're going to look up the start of the array for Q in this table. So essentially, this lookup function takes Q and comes out with this order pair, which tells you which array Q points to. Now, once you have this, you can do runtime check just like in Java. Okay. Yeah. So, but the big advantage of this technique is that it's backwards compatible. Pointers are just like normal pointers. There is no metadata involved with each pointer. But the problem is you're going to store all allocations in one global table, and the table can go very big, which means that your lookup overheads are going to be a lot worse. And people have reported overheads up to 11x slowdown using this technique. Now, our solution to this problem is simple. Let's go back to this Jones and Kelly solution. Let's say instead of this one big table, we have two small tables. Okay? And the entry for Q, let's say we know for a fact that it lies in this table. Then we can look up this table and get the referent for P. And since we have a smaller table, our lookups are going to be faster. Let's say in generalizing this idea, if we split the heap into disjoint subheaps, we can maintain one separate table per subheap of the program. And since each table is now smaller, our lookups are going to be faster. Okay. And how do we split the heap? Well, we use automatic pull allocation. Okay. And we can now maintain one table per pool. We can do several other optimizations, basically entering only array objects, because automatic pull allocation also has information about types. So this will help you enter only array objects into the table, not every object. And this actually speeds up. And we also support pointers which go out of bounds and that come back efficiently, but I'm not going to discuss that. If you're interested, you can read our paper in ICCO6. In the results, we measured on the same old-end benchmarks and 3 Unix daemons. And the maximum overhead we found was for this program, which is like 69%. Okay. The same programs, if you had run it using the Jones and Kelly technique, we found that the overheads were up to 3x and 4x slowdown. And we are also able to detect some known attacks from this suite of vulnerabilities, which actually models vulnerabilities from reported vulnerabilities from bug track. Yeah. 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 Yeah.
All those go to one.
Yeah. So the idea is that if you used Jones and Kelly for a solution for the same program, you would have much worse overhead, because you're not only clubbing these arrays, you're also clubbing them with all other allocations in the program. Yeah, you would have a definitely very bad performance overhead. But the point is that there aren't that many programs which do such million array allocations in one program. So this FTPD is like 20,000 lines of code, 25,000 lines. The rest are like really small. Yeah, so you're right. If you have a custom memory allocators, everything will look like a TU pool, and we'll have one big blob, and it will be a TU pool. And we don't. This automatic pool allocation doesn't support custom allocators out of the box. You go and perhaps one solution for that is go and annotate. What are the custom memory allocator functions. That's. Second thing is, if you had more TU pools, you can always go and restructure your program, write in a more type-safe manner, make sure that there are not that many. But we won't recommend. The idea here is to make sure that the porting effort is not higher. So we haven't done that yet.
So how did you actually do this? Like, you didn't quantify how you actually build the table. So what did you actually do?
So we do what Jones and Kelly does. The table is organized as a tree. It's called a splay tree, and the lookups are, the splay tree has this important property that it'll, once you do a lookup, it'll rotate the tree so that the last lookup is like on the top, so that next time you do a lookup, you can easily get the element from the top. So we do exactly the same. It's we don't make any changes with that part. We do that optimization that I've talked about earlier, that we don't enter array objects into the table. In case of Jones and Kelly, they don't know which objects are going to be used as arrays because they don't do any static analysis. It's just a runtime technique. So in our case, our tables are smaller because we only enter array objects.
You mentioned that there was previous code attack up to 11.
Yeah.
Did you test it with
No, not those benchmarks. But we applied that same technique on these benchmarks. And we got like 3x to 4x slowdown. It's not 11, but still.
So the automatic allocation technique required alias analysis, right?
Yeah.
So that alias analysis is required to automatic allocation, right?
It's not invented. Yeah. Yeah.
It must have. So would it be fair to say that SAFECode makes precisely that alias analysis?
SAFECode does make that alias analysis sound, and SAFECode can make any other alias analysis which has those properties that I talked about as sound. And summarize, we have a backwards compatible bonds checking technique which is automatic and it has a low overhead compared to other approaches. And I'm going to spend very little time on the last part of this talk, efficient dangling pointer detection. We all know what the problem is. Well, accessing memory after it's free. So we have a free here and trying to access it after the pointer is free. And the previous solutions are basically avoid this problem using garbage collection or use some heuristics which sort of delay the reuse of memory, which don't give you any guarantees, which will again increase memory consumption of the program, but still are used by many debugging tools. So there is some sort of a tension between the amount of memory consumption that you can tolerate and the ability to detect or prevent dangling pointers. Okay. And there is one previous solution which is actually used by electric fence on Windows, electric fence on Unix, and page heap on Windows also does this, is to use memory management unit to detect dangling pointers. And the way this works is simple. So we're going to use a new virtual and physical page for each allocation of the program. Okay. If you have q is equal to malloc, you're going to use a new virtual page here and a new physical page here to do this allocation. And if you have another allocation, say r is equal to malloc, you're going to use altogether new virtual page and altogether new physical page for this allocation. Right? Once you have that, when you free R, you can change permissions on the individual virtual pages, and your dangling pointer is detected at runtime. Okay. The big advantage about this technique is that it does everything using hardware checks, right? And there is no metadata involved for any pointers, so it will work out of the box in some sense. But there is a big disadvantage, which is that memory consumption is going to blow up. You're going to use one virtual page for each allocation of the program, and one physical page for each allocation of the program. And our technique basically first solves the physical page issue by using this. So we're going to use a new virtual page for each allocation, but map it to the same physical page as the original program. Okay. So if you have a q is equal to malloc, it's going to look like this. You use a new virtual page, and obtain some physical memory. And if you have r equal to malloc, we're going to use again a new virtual page, but map it to the same physical page so that we can use the underlying physical memory. Now we can change permissions on virtual pages just like earlier when you have a free, and detect dangling pointers just like earlier. What we have done is basically shared these physical pages via different virtual pages and are able to detect dangling pointers with the same physical memory usage as the original program. Okay? So we have removed one constraint, which is that the physical memory consumption is going to blow up. But still, we have this address space usage problem. We are going to use a lot more virtual pages than the original program. And it's in some sense we have pushed the problem from the actual physical memory usage to sort of address space usage issue. And we can alleviate this problem using automatic pool allocation. Yes. Are you increasing what? Physical? Yeah, but we are going to use the same physical page, but use different virtual pages. So this virtual page maps to this physical page. There is a different virtual page, which again maps to the same physical page. Yeah, it doesn't matter if you put several objects in the same physical page. But we're going to use one new virtual page for each allocation. Well, it's automatically done by the operating system. So operating system maintains this physical to virtual address mapping, and there is a TLB which usually speeds that up. So it maintains essentially a cache of this map, and then speeds that up. So no, we don't have to change. I mean, you could. Yeah. Yeah, different offsets in the sense. Yeah. So we're going to use pool allocation to reclaim some of the virtual pages. We already know that pool allocation binds the lifetime of some of the pools, right? Once you know that a pool is never going to be accessed again, you can reclaim all the virtual pages that are tied up by the pool and then use it for other pools. Okay, so we're going to alleviate the problem of address space usage. And if you have a long-lived pool, we think that it's unlikely to cause a problem on 64-bit machines where there's plenty of address space available. On server applications, we found that we can reuse virtual pages after each request because logically speaking, any memory used in one request is not going to be needed in servicing another request. But there are limitations, and every allocations and deallocation is going to use a system call, right? So normal malloc does a system call every so often and tries to use the memory that it gets from out of one system call. But here, since we want a new virtual page for each allocation, we are going to do a new system call for every allocation, a new system call for every deallocation. And moreover, there will be more increases in TLB misses because we have more virtual pages to physical pages. Right? And for programs with high frequency of allocation and deallocation, the overhead is just too high. Okay? But we are working on some architectural improvements to the TLB which can alleviate some of these problems. I mean, remove some of the overheads and in making these system calls, or basically make sure that you don't have as many TLB misses. I'm not going to talk about that. In results, well, again we evaluated on some Unix utilities and found that the overhead was less than 15%. And for servers, we found that the overhead was less than 4%. Okay. But for allocation intensive benchmarks like Olden, we got like 11 times slowdown, just because of the system call overhead and the TLB misspin. But you could still use our technique to debug those applications. To summarize, we don't have any physical memory usage, and because of pool allocation, we have less address space wastage. And for some applications, the overhead is good, less than 15%. For others, we found that it slows down up to 11 times. Purify detects hanging pointers only heuristically. So I don't think it. So some other work I've done is basically memory safety for embedded programs, some of which I've already talked about in this talk, and doing a path-sensitive data flow analysis using iterative refinement, which I worked with in the ESP group here over the summer. In future, the things I like to work on is basically use SAFECode techniques and operating system components. This is a project that we just started. It's in a preliminary stage. Okay. And I want to work more on guaranteeing other properties using static analysis plus runtime techniques. Okay. Techniques like protocol errors or data races. And as I've hinted at in the DSM work, I'm also interested in looking at architectural improvements for efficient runtime. Summarize, SAFECode provides a memory safety guarantee to production C code. It does with low overhead. And it also is a sound analysis framework for C because we have defined sound operational semantics for C based on alias analysis and call graph information. Improve reliability of C software that way. And finally, SAFECode also improves programmer productivity because we have this. Some of our tools can also be used as runtime debugging tools, right? Like the dangling pointer direction technique or the bounce check technique. We also have some static debugging tools which I've not talked about. That's it. Yes. Yeah. Yeah. So one of the things that I didn't talk about is how that alias analysis also maintains offsets for each pointer. So if you have struct within a struct, but still, we know at what offset things are, what offset which struct is there. In most cases, alias analysis is able to figure out that, and it doesn't, generate a TU node. So in some sense, alias analysis doesn't actually depend on where you do cast in the program. It depends on how you use the memory object, right? If you use certain portion of memory at certain offset as one type, and it doesn't change even because you have embedded structs, then it won't result in a TU. Yeah, that case is possible, definitely possible. Yeah. Yeah. We're checking that pointer points to somewhere in the pool. We don't care where exactly. In case of TU pool, we just are sort of sandboxing that pointer to point to somewhere in that. So one answer is that, yes, if you could take your programs and port it to Java or C# or any of the safe languages, well, you should. I mean, if you can, you should. But the point is there exist too many of these applications which are written by programmers who left their companies years ago. And it's difficult to do the porting just because there are so many of them. Right? So my thing is that I would be surprised if, I don't know, I mean, maybe I should claim that. But in future, we are going to see more and more applications in safe languages, written in safe languages than in unsafe languages. But I don't know if porting of these unsafe languages to safe languages is going to happen anytime soon. So, like I told you, but unification based, we have a solution which basically based on metadata for each pointer. It works, but you need to port your application by adding this metadata. But in case of flow sensitivity, we don't yet have any solutions. I often don't know of any simple way to actually extend our approach to flow sensitive alias. Yes.
What's the largest C program?
It's the FTPD program which had like 25,000. So most of it is like infrastructure issues where our alias analysis is not yet strong enough to deal with larger programs, or our pool allocation has some problems in dealing with some of these larger programs like SSH daemon, for instance. We have tried that and found that alias analysis crashes because of some bug, which is a bug in alias analysis. It's mostly infrastructure issue. There are some other problems in some sense which could arise because when you're doing alias analysis for a program, you could have memory that is allocated outside your program, like a memory allocated in the libraries and written to your program. Our alias analysis just says that these are like, I don't know where they came from, but I think those types is, the type of these objects is such and such. In those cases, well, what we do is not really sound because we can't check them if they're not pool allocated. So in some sense, there is some issue there that we need to take into account and move on to this larger program. Any more questions?